first talk we have Luca Trevisan, who will talk about generalizations of Cheeger's inequalities.
Yes, thank you. So this is about some new recent work in spectral graph theory. So the study of applications of linear algebra to the study of graph properties and graph algorithms. So the connection between graphs and linear algebra comes from the fact that one can very naturally associate matrices to graphs, most naturally the adjacency matrix of a graph. And as has been known for a long time, there are several connections between linear algebraic properties of the adjacency matrix and combinatorial properties of the graph. So the eigenvalues of the matrix say several interesting things about combinatorial properties of the graph. And usually those connections have constructive proofs, which show that given the eigenvectors of the adjacency matrix, one can also construct efficient algorithms for graph problems. In fact, inside of the adjacency matrix, it's often easier to work with a normalized version of the adjacency matrix. It's called the Laplacian. And this matrix is symmetric if the graph is undirected. So that means that all the eigenvalues are real. And here are some basic facts about the eigenvalues of this matrix and how they relate to combinatorial properties of the graph. And then we will explore various generalizations of those basic facts. So one effect of this normalization is that regardless of the size of the graph and the degree of the graph, all the eigenvalues of this matrix are between 0 and 2. Without the normalization, they would be in a range that depends on the average degree of the graph. And also, 0 is always achieved as an eigenvalue, 2 may or may not. So two basic facts have been known for a long time, but are already fairly surprising, are that the number of times that 0 occurs as an eigenvalue of this matrix, so the multiplicity with which it occurs, is precisely the number of quantity components of the graph. Okay? So 0 occurs always at least once, and if it occurs twice, the graph is disconnected. If it occurs exactly 4 times, the graph has precisely 4 quantity components. The other fact is that on the other end of the spectrum, 2 may or may not be achieved as an eigenvalue, and it's achieved only when the graph is bipartite, or one of its connected components is bipartite. So two of the most fundamental graph properties, connectivity and two-colorability, are captured by the list of eigenvalues of the Laplacian matrix. They're also captured by the list of eigenvalues of the adjacency matrix, but this normalization makes the statements cleaner.
Strictly less than 2, what does that say?
Well, then it says that none of the quantity components of the graph are bipartite.
Does it give you a measurement of some kind?
Well, thanks for this question. My first work in spectral graph theory was to show that the gap between 2 and lambda n, if any, shows how far from bipartite are all subset of vertices of the graph. So if there is a gap for every subset of vertices, for every way of trying to bipartite them, there will be some violating edges. And if this gap is epsilon, an epsilon fraction of those edges will be violating. Conversely, if the gap is small, it's possible to find a subset of vertices that is almost disconnected from the rest of the graph and that is almost bipartite. And the number of violating edges will be root epsilon as a fraction of the total if the gap here is less than epsilon.
Does it say anything about the degree of
The degree?
Yeah, if lambda, if the last eigenvalue is strictly less than 2, you say it measures how far it is from being bipartite. Yeah.
Yes.
That's it.
That's a characterization.
So that, okay.
So to see some example kind of things that one can just read from the list of eigenvalues. If I tell you that I picked some graph and I computed the list of eigenvalues and it's like this, you can already say, well, this is a graph with 10 vertices because there are 10 eigenvalues. It's connected because 0 appears only once, and it's not bipartite. In fact, this is a graph that has those eigenvalues. While if you look at the graph with this list of eigenvalues, you can say that it has precisely 2 quantity components, and that neither of them is bipartite. and that it has 8 vertices. While a graph that has this list of eigenvalues, it's a graph that is connected, and it is bipartite. Okay. So let me describe the proof of the characterization of the number of quantity components of the graph as the number of times that 0 occurs as an eigenvalue, because that will be something that we will then look at various generalizations of. So the best characterization of eigenvalues to work out this connection, it's not as roots of the characteristic polynomial, but as solutions of optimization problems in the variational characterization, which is true for Hermitian matrices, so in particular it's true for real valued matrices that are symmetric. And when we have an undirected graph, its adjacency matrix and its Laplacian matrix will be real valued matrices that are symmetric. Okay, so if a matrix is symmetric and real valued, then all the eigenvalues are real. If we list them with multiplicities, then the kth smallest eigenvalue is characterized this way. It's this optimal solution of this min-max problem, where you look at many possible vectors that all of them making this ratio small. So lambda k is the minimum overall k-dimensional choices of vectors for which the quadratic form normalized by the norm of x is all small. And the optimum space for each k is spanned by the eigenvalues of lambda 1 up to lambda k. Now the Laplacian matrix is sort of reverse engineered so that this quantity over whose optimization gives the eigenvalues of a matrix has a nice form in terms of the graph. So the quantity that one optimizes to compute the eigenvalues of the Laplacian, it's something where for a given vector, you look over the edges of the graph, how much the vector gives different values to the endpoints on the edge. So the average of this distance square, normalized by the summation of, a sort of L2 norm of the vector, but normalized by the degree. Okay. So this means that the eigenvalues of the Laplacian, they are the min-max solution of with this cost function. And notice that this cost function can be 0 only when, or precisely when, x is a vector that is constant on quantity components of the graph. Because for this quantity to be 0, it's a sum of squares, every term must be 0. So that means that for every edge, xu and xv must be the same. So for every path, all the vertices along the path must be the same. So for every quantity components, all the vertices in the quantity components must be the same. So if a graph has k or more quantity components, you can immediately see that lambda k is 0, because as a k-dimensional space A solution to this problem, we can pick the space of all vectors that are constant on quantity components. So this will be k-dimensional or more, and for all of them, this quantity will be 0, so the maximum will be 0. So if you have a graph with k or more quantity components, lambda k of the Laplacian will have to be 0. The other direction is also easy to show, but I want to show sort of not the shortest proof, but one that will give some intuition about various generalizations. So suppose we have a graph in which lambda k is 0. We want to show that there are k or more quantity components. Okay. Now let's look at the eigenvectors of lambda 1 up to lambda k. So those will all be vectors in this space A, for which this max is 0. So these will all be vectors for which this expression is 0. So those are all vectors that are orthogonal to each other and that are constant on quantity components. Now, define this mapping of vertices of the graph into a k-dimensional real space. Okay? So every eigenvector is associating a number to each vertex. If you have k eigenvectors, you have k numbers for every vertex. So think of this association as being an embedding of vertices into a k-dimensional space. Now, when you look at each coordinate of this mapping, so that coordinate will have to be the same value for for every two vertices that are in the same quantity component. So in fact, the whole mapping will have to give the same output for two vertices that are in the same quantity component, because this will be true coordinate by coordinate. So if two vertices are in the same quantity component, this mapping maps them to the same point. So if you have two vertices mapped to two different points, they must be in different quantity components. Okay. Now, how did we get this mapping? So we started from those k n-dimensional vectors. So just think of them as being, kind of k row vectors of dimension n. And then we turn this k by n matrix around, and now we have n k-dimensional vectors, and those are our points. Since those k vectors are linearly independent, this k by n matrix has full rank. So it cannot be that when you look at its columns or rows, once it's flipped over, you only see k minus 1 different rows. This would violate the rank condition, would easily make you find the linear dependency between those vectors. So this mapping must map points to at least, must map vertices to at least k different points, and the pre-image of each of those points is a distinct quantity component, or union of quantity components. So you have at least k quantity components. All right, now we want to look at various ways in which this connection can be generalized. Particularly, so this is an extremal result. It says the smallest that an eigenvalue can be is 0. And if lambda k is 0, here it's what happens. We have k quantity components. So a robust version of this result would be something that characterizes the cases in which lambda k is small instead of being 0. And so that's what we want to talk about. So in order to talk about this, we also need a generalization of the notion of a set of vertices being disconnected from the rest of the graph, and kind of a quantitative version of this. And the notion of conductance will work well in this connection. So if we have a set of vertices in a graph, its conductance, it's the fraction of edges incident on the set that leave the set, roughly. So it's a number of edges that leave the set divided by the sum of the degrees of the vertices in the set. An operational way of thinking about it is that if we pick a random vertex in S and then move with probability proportional to the degree, and then move to a random neighbor, the probability of leaving S is precisely the conductance of S. And then the conductance of the graph, it's the minimum overall partitions of the vertex set into two parts of the conductance of the small side of the cut. So for example, this is a graph of conductance 0. This set has conductance 0, and so that's the complement. This is a graph of small conductance, but asymptotically the conductance of an n cycle is order 1 over n. And this is a graph with fairly big conductance. The smallest conductance set is this set of 5 inner vertices. The total degree is 15, and there are 5 edges going out. Only as much as a third of the edges is coming out. And notice that here the second eigenvalue is fairly large, while here the second eigenvalue was fairly small. Actually, this definition of conductance of a set defines an optimization problem of finding the smallest conductance set, which is fairly interesting in its own right. So if, for example, the undirected graph describes a social network, then a low conductance subset of the graph is, say, a subset of conductance 0.1, a set of users that on average have 90% of their friends in the set. So it's a very tightly bound community. And if a graph is constructed starting from a data set by having one vertex for each data item, and then the weight of an edge to be a measure of similarity between data items, then the low conductance set is a set of items that are much more similar to each other than to anything else. So in some cases, this is an appropriate definition of clustering. And also, in some cases, finding balanced low conductance cuts can be useful to get exponential time, but sort of faster than brute force algorithms for NP-hard problems. For example, in planar graphs, one can solve most hard problems in time 2 to the root n because of the fact that one can always find cuts of conductance order of 1 over root n. And in general, finding low conductance balanced cut can give significant improvements over brute force. Okay, so one way in which immediately one can see the conductance relates to the spectrum of the graph is that one can have a non-trivial multiplicity of 0 if and only if the graph is disconnected. A graph is disconnected if and only if there is a cut of conductance 0. So lambda 2 and the conductance are 0 exactly in the same cases. And the Cheeger inequality for graphs states that the conductance of a graph and the second eigenvalue of the Laplacian, they are sort of approximations of each other. Okay? So one is small if and only if the other is small, one is large if and only if the other is large, up to this quadratic gap, which is tight. And the proof of the upper bound is constructive in the following sense, that given an eigenvector of lambda 2, in fact any vector for which the Rayleigh quotient is small, one can run the following algorithm. So this vector will give an assignment of numbers to vertices, use these numbers as keys to sort the vertices, and then consider all the initial segments of the sorted order, and pick the initial set of vertices for which the conductance is smallest. This set will be a set of conductance at most square root of 2 lambda 2. So in particular, the graph will have conductance at most this much. But because of the other direction of the inequality, this also says that the set found by this very efficient algorithm has conductance that is at most 2 square root of the optimum. So this is also an approximation algorithm, which in fact works very well on average, usually better than predicted by this inequality, even though there are graphs for which this is tight.
You have to find the vector.
Yes, but with the new Laplacian solvers, you can do even that in nearly linear time. So there are many ways in which these inequalities are useful, so they used by different communities. One way is that it's a worst-case analysis of this algorithm that sorts vertices according to the eigenvector of lambda 2. This is an algorithm that was suggested by Fiedler even in the 70s before this analysis. To construct expanders, so graphs of large conductance, usually the analysis of the proof that the graph has large conductance is the hard part, and it's often convenient to reason about the spectrum of the graph instead of reasoning about the conductance. But some other times the opposite is true. So it's known that to analyze the mixing time random walks in graphs, so what one needs to compute is lambda 2 of the Laplacian of the graph of the and in some, but lambda 2 and the conductance are approximations of each other. So if one wants to prove that random walks converge quickly, which means one needs to prove a lower bound on lambda 2, in some cases it can be easier to prove a lower bound on the conductance, and that's how, say, with the method of the canonical paths, and sometimes this is easier. Okay, so coming to our work, we were interested in getting a robust version of the fact that lambda k is 0 if and only if g has k or more kinetic components. The Cheeger inequality is a robust version of this for k equal 2. That says lambda 2 is small if and only if g can be partitioned into, the vertices can be partitioned into two sets, giving a cut of small conductance. And our result, qualitatively, is that lambda k is small if and only if one can find in the graph k or more disjoint sets of vertices, each one having small conductance. Okay? So for k equal 2 is the Cheeger inequality, for larger k gives a new characterization. So to make this qualitative statement quantitative, we define generalization of conductance. so we call the order k conductance the minimum overall choices of k disjoint sets of the maximum conductance of the sets that we picked. Okay? So the order k conductance is small if and only if you can find k disjoint sets each of small conductance. And for k equal 2, that's the conductance, and for larger k, one observation is that this quantity is 0 if and only if G has k quantity components or more. Yeah?
Should S1 k form a partition or something?
Both definitions are interesting. The two numbers are off by a factor of k. So for example, this is a graph of large order 3 conductance, even though it has conductance 0. When you try to divide this graph into 3 parts, at least one part will have many edges leaving. This is a graph for small order 3 conductance. So quantitatively, our theorem is that the order k conductance and lambda k are approximations of each other up to the same quadratic loss that comes up also in the Cheeger inequality, and then this other loss, which is order of k squared. This can be significant when one looks at, say, the root nth eigenvalue. And the upper bound is constructive, meaning that if one gives us the eigenvectors of lambda 1 up to lambda k in nearly linear time, in the size of the graph, polynomial time in k, we can find the k disjoint sets that witness this upper bound. And if you allow some gap between how many sets you're looking for and how many eigenvalues are small, this loss of k squared becomes root log k, which is known to be best possible. This was also proved by Luis Raghavendra, Tetali, and Vempala. So one aspect of the proof, both our proof and the proof of Luis and other, is that it says something, although so it doesn't give a complete analysis, but it says something about an algorithm for clustering that works very well in practice. So this is an algorithm that does the following. It's given a graph and a parameter k. Then it computes the eigenvectors corresponding to the smallest eigenvalues of the Laplacian. Then computes the mapping that I also defined before when I was proving that when lambda k is 0, you have k quantity components or more. So it uses those k eigenvectors to map vertices into k-dimensional points. Then it forgets all about the edges of the graph, just looks at this set of endpoints in k-dimensional space, and it tries to cluster them into k clusters with some geometric algorithm. Usually they apply k-means. So this is an algorithm that comes up in, so that part of computer science doesn't work quite like theory, where we start from a problem and then we design an algorithm and then we prove or show by experiments that the algorithm solves the problem. This is more like there is a lot of data, then we apply this algorithm to the data, the results are interesting, and then that means that the algorithm works. But it's not like there is a problem and the algorithm solves the problem. But one thing that this algorithm does provably is the following. Suppose that you construct a random graph in the following way. You start from 3 disjoint sets of vertices. Here I draw them with different colors. And then you pick edges at random, but with high probability within the same set and with low probability between. So here the probability of edges between different colors was 2%, inside was 20%. Just to get an example. Now, take this graph and find and apply this algorithm for k equal 3. So this will find the 3-dimensional mapping of vertices into a 3-dimensional space. And this is what this mapping will look like. In these mappings, one dimension always maps all vertices to the same constant. So a k-dimensional mapping is really intrinsically k minus 1 dimensional. So a 3-dimensional mapping is actually this mapping in the plane. The algorithm that does this mapping has no idea what the colors of the vertices are, it just sees a graph. But it does tend to push together the vertices that we connected with high probability and to push apart the vertices we connected with lower probability. So if you now forget about the edges and just apply some geometric partitioning algorithm, maybe with a couple of outliers, you will find out what were the 3 sets that you started from. So in fact, this can be established rigorously, that if you plant a k clustering in a graph by starting from k sets, connecting within sets with high probability, between sets with low probability, this mapping will tend to push vertices in the same cluster together, vertices in different clusters apart, and then facilitate geometric algorithms. But what I think would be interesting to understand a little bit better is, for general graphs, what problem is this algorithm solving and why it tends to work well. So both in our proof and in the result of Lewis and others, when we want to find k low conductance sets whenever they exist, the first step of our algorithms is to do exactly the same mapping. Then we don't apply k-means to this mapping. What I do is more like partitioning the space into k cones and then taking each of them. We partition it into many more cones and then patch them together. But it does give at least a first understanding that for arbitrary graphs, this mapping is discovering something. And then applying geometric algorithms to this embedding is a sort of sound process. Alessandra, you had a question?
Are you saying that for this random-ish graph, or random graphs, I guess, with different probabilities, it recovers exactly the planted?
Well, it depends on the exactly the difference in probabilities between.
Yeah, of course, but how much is the, let's say P is the probability within each color and Q is across. What's the difference that it recovers exactly with high probability?
Maybe it has to be like log over root n. I'm not sure. There is a paper by Ang, Jordan, and Weiss where they actually give a more general analysis. They say, suppose you have a graph, and in your graph you have k sets of vertices. Each set of vertex is an expander. Within sets of vertices you have few edges, but then I don't remember what are the thresholds. But each set of vertices is an expander. Between sets you have few edges, and then there is a technical thing like in every set, every vertex has more neighbors inside the set than outside the set. Under those 3 conditions, this algorithm will find the sets exactly.
Okay, but this is pretty, I remember that this was with matrix perturbation.
Yes.
So it's pretty weak in the sense of the parameters.
It will not work with very sparse graphs.
Yeah.
Yeah.
Depends on the size of the clusters, right? As you can encode quantity.
Let's say they're equal.
Then I think it's 1 to the root n.
This one.
1 to the root n. The difference in probabilities.
Okay. Traditionally, the speaker talks, and so let's sort of.
To the conservative.
Yeah, sometimes, yeah. Okay. So let me state one more result, then we can talk to each other in the break. So coming back to the Cheeger inequality, the standard case for k equal 2. So as I said, this quadratic loss is necessary for some graphs, but it seems to, so this worst case analysis seems to not do justice to how well the algorithm works in practice. So the other result I want to talk about is a bit tightening of this inequality, where we show that for every k, the conductance of the graph is always at most order of k times lambda 2 divided by root lambda k. So when k is 2, that's the same inequality. Actually, this constant maybe will become 8 instead of root 2. But this is saying that if you have a graph where there is a sparse cut, so lambda 2 is small, but maybe lambda 5 is fairly large, maybe it's an absolute constant, then what you get is a constant factor approximation, where the constant will depend on how large is k and how large is root lambda k. And the upper bound is achieved by the standard algorithm, the one that uses only an eigenvector of lambda 2, doesn't know anything about lambda k or about eigenvectors of lambda k. So this is also an improved analysis of the sweep algorithm. It says the set found by the sweep algorithm is such that for every k, its conductance is at most the optimal conductance times, this is something like 2 root 2 or maybe 4, like it's a really small constant, times k divided by root lambda k. And the algorithm doesn't know anything about lambda 3, lambda 4, and so on. So if you have a graph for which for some k this ratio is bounded, that's a graph on which the sweep algorithm will do better than the standard analysis.
Now this O of k, the O, what does it refer to?
It's an absolute constant. This is like 4 times k times lambda 2 over root lambda k.
4 times k times O.
I think it's 2 root 2, but it's no more than 10.
It's not a different constant for every k? Or?
No, order of k. Come on.
Number of vertices of the graph.
No. This is like no more than 10 times k times lambda 2 over root lambda k.
There's no tilde. Maybe that's what you meant. There's no tilde or no. So it is a constant.
Yeah.
No, it's a number for which we have a name.
Okay. No.
Yes, it's no more than 10. Okay. So let me. Okay. Right. So so the proof goes through a structure theorem that maybe is interesting on its own, which says the following: for every so if x is an eigenvector of lambda 2, it's always possible to find some other vector y that is not too far from x if lambda k is bigger than lambda 2, and such that y, when you look at its entries, contains only 2k different values. Okay? So if there is a big gap between lambda 2 and lambda k, the eigenvector of lambda 2 is kind of discrete. It's sort of close to having not too many different values. Okay? So that's not the way the eigenvector lambda 2 in a cycle looks like. Like there, when you look at the various entries, you sort of see a smooth, if you sort them, you see a very smooth growth. While in graphs in which there is a gap between lambda 2 and lambda k, so if you sort the vertices by value, you're going to see chunks, or so up to some noise. Okay. And then,
It's the sinus.
what's that?
For the cycle, it's the sinusoid. It's just a sinus.
If you sort vertices by how they appear in the cycle, yeah, it's a sinusoid. If you sort vertices by the value they get in the eigenvector, you'll see a smoothly growing function. So then the second part is that,
Sorry,
yes.
So by 2k value vector, you're talking about the coordinates of y.
Yes.
Yeah, if you look at the coordinates, the values of the coordinates of y, you only observe at most 2k different values. And then the second part is that if you apply the sweep algorithm to an eigenvector x that is chunky in this sense, that can be well approximated by a discrete vector, then you get some improvement over the standard Cheeger inequality. So in particular, if this distance is very small, the quadratic loss sort of disappears, and you just get order of k times lambda 2. If this approximation is poor, you still get root lambda 2 as usual. So those are the... so when you combine those two together, you get the statement that I claimed. Okay. So for the first part, which I think is more interesting, this structure theorem, some intuition for why something like this might be believable is to look at what happens in the extremal case. So the biggest gap you can have between lambda 2 and lambda k is that, say, lambda 2 is 0 and lambda k is positive. So then this ratio will be 0. So what happens when lambda 2 is 0 and lambda k is positive? So then x is constant on kinetic components. But if lambda k is positive, you only have k minus 1 kinetic components, or fewer. So x can only have k minus 1 different values. So you don't need any approximation to say that it has only k minus 1 different values. Right? So it's a distance 0 from some vector that has only k minus 1 different values. So what we need to prove is a robust version of this. so the proof sort of works in the following way. We again think of the eigenvector x as being a mapping of vertices to the line, and then we divide the line into 2k intervals.
How does it map the vertices on the line?
Oh, well, it's a vector with one coordinate for every vertex. So you have a real number for every vertex. You can think of it this way. So then we divide the line into intervals. And so in a way that will make sure that within each intervals the points are roughly equally far from the boundaries. There's some technical I want to get into. And then we will construct the approximating vector by looking for every vertex, where it's mapped on the line, and what's the closest interval boundary to it. So then what we need to argue is that if lambda k is large, this rounding will not require a lot of moving around of vertices. Will not create a new assignment of real numbers to vertices very far from what we had before. And equivalently, what we need to show is that if this rounding requires us to move a lot, we can find a witness that lambda k was small. And we find the witness lambda k is small in that case by finding k disjointly supported vectors, each of them having small Rayleigh quotient. And basically, each of those vectors will be supported meaning non-zero, only on the vertices that belong to each of the intervals. And so when you need to move, when you have lots of intervals where lots of points are far from the boundaries, this process will construct vectors with small Rayleigh quotient. Okay. Then for the other result, so this is what we need to show, that if we have a vector x approximated by some other vector y that has only a bounding number of distinct values, the performance of the sweep algorithm will be kind of with a quadratic loss but multiplied by the distance, and then a linear loss, which would be optimum. And what we have to work with is the standard proof that gives always a quadratic loss, regardless of distance, and an observation that if the vector x itself has only k different values, when you do the sweep algorithm, you only lose a factor of k. So somehow we need to bring together the ideas in this proof and in this proof, and this is sort of an interpolation of the two arguments. Actually, maybe I should have let people talk because I'm going a bit faster than I was planning. Sorry. So another kind of question that I want to briefly mention is to get a robust version of this statement. Okay? So the characterization of number of quantitic components in terms of multiplicity of 0 says that you have that lambda k of the Laplacian is 0, lambda k plus 1 is positive, precisely when G has k quantitic components. Okay. So a robust version would be a characterization of what happens when there is a big gap between lambda k and lambda k plus 1. Or say what happens when lambda k is small, lambda k plus 1 is large. So it was a result of Tanaka that proved that with a large enough gap between lambda k and lambda k plus 1, so this gap needs to be quadratic but also exponential in k. So then the following happens, that so we know that when lambda k is small, we can find k sets of small conductance, and so he does. But then with this condition, we can also show that each of those k. So first of all, he gets a partition, and each of the sets in this partition induces a subgraph that has large conductance, large dependent on lambda k plus 1. Okay? So what you get is that the graph looks like there are k sets of vertices. Each one induces an expander, and each one has few edges coming out. So that gives a pretty strong structure theorem for what the graph looks like. It also says that you cannot hope to get a partition into k plus 1 sets, each of small conductance, because any such partition will need to break one of the expanders.
But this looks, isn't it a fairly strong assumption of the eigenvalue? That lambda k
Yes.
plus 1 is bigger than 5k plus
Yes, it is a strong assumption, but there is also a strong conclusion. So to some extent, one would guess that. But it's true. It's strong in two ways. There is a quadratic gap between lambda k plus 1, and then this exponential means that when k is more than log n, this statement is not really saying anything.
So how tight is this?
We don't know. But
It's like winning the lottery. It's unlikely, but you'll be very happy if you get it.
What's the meaning of induce here?
induce means that you look at a subgraph that has the vertices in that set, and then all the edges that have both endpoints in that set. So it's vertex induced. Yes?
I'm not sure if it makes sense, but is there any chance this might follow from what you already proved about like lambda k being small, then you have k components, and from the result you first mentioned at the beginning of the talk?
Yeah, no, it's not at all clear that each set needs to be an expander.
Combined with lambda k plus 1. Oh, I see.
Even if lambda k plus 1 is big, it's not clear.
Right, you get
I mean, somehow, if you know this, then you know that it has to be the case, because then the partition is unique. But from our argument, it doesn't really follow that the subset needs to be an expander. And also, this argument is very non-constructive. I mean, not non-constructive, it's non-algorithmic. He finds this partition by repeatedly finding cuts of optimal conductance. And in the argument, he needs the cut to be of optimal conductance to get some contradiction later. Okay, so in a kind of recent work we just completed, we get something somewhat tighter in the following way. So first of all, if we have a gap in the order k conductance versus order k plus 1 conductance, this gap can really be arbitrarily small. We get the same conclusion. So there is a partition into k subsets. Each subset is a subset of low conductance where low depends on phi k, and each set in this partition induces a large conductance subgraph where large depends on phi k plus 1. Okay. And this we prove by a non-constructive argument. Anyway, it's also a condition that we don't know how to test. Those are all NPR to compute quantities. But with a sufficiently large gap between the eigenvalues, we can recover the conclusion algorithmically. As in Tanaka, we have the quadratic gap. It's still not clear if this quadratic gap is necessary, but the dependence on k goes from exponential to polynomial. And here, this was exponential time computation, this is a polynomial time computation.
But
Yeah.
this does follow from your previous result, right?
No.
To get this inequality, to get the sufficient condition from the...
Sorry, we use the previous result, but it also needs something more. So we still don't know how to say that what we get from the previous result is a collection of sets, each of them inducing an expander. But then we do a post-processing that will enforce that.
You try to convince him that he can get a weaker result and he refused. So now you try to convince him that he can get a stronger result.
No, I just meant...
Yeah.
Okay, maybe I'm wrong, but the lambda k plus 1 condition,
Yeah.
so that implies the previous one, right? That the phi k plus 1?
Yes.
Okay, so that's using your result. Or
Yes. So once we approve this,
something more easier.
once we approve this,
Yes, that's forcing it.
our previous result implies that under this condition, then the existence of the partition follows. However, it doesn't follow that we can find it algorithmically, because it could still be that that partition is not the same that is found by the algorithm. So that's it.
But can you generate example? First of all, this O should presumably be omega, but
Yeah, I mean, there is a yeah, there is a constant for which this is true.
About the coefficient, but is this achievable? Are there graphs where this happens? You get such? Is it possible?
No, we don't. I mean.
No, I'm asking: is it possible is it possible for the spectrum to really give?
Yeah, you can make the spectrum jump as much as you want. Like if you.
A bunch of expanders.
Yeah.
I see. So you just glue together weekly.
Yeah, I mean you can have lambda k be 1 over n and lambda k plus 1 be a constant. You can do whatever you want. It could be right. Then we. Then we always knew how to reason. Yeah. Yeah. Yes. Okay. So I'll mention one more kind of point of view on the generalized Cheeger inequality that I described before, which is that that improved analysis of the Cheeger inequality, that's improved only if it's a graph in which lambda k is large for some k. Otherwise, that ratio k lambda 2 over root lambda k is not better than the original analysis. But graphs in which lambda k is large for small k are graphs for which we know several algorithms that perform better than general graphs. And in fact, for a sort of pretty weak notion of large, one can find constant factor approximation or even 1 plus epsilon approximation for minimal conductance sets in time that is exponential in k. So we could see this improved analysis of the sweep algorithm as a kind of trade-off where instead of getting this constant or 1 plus epsilon approximation, we get some k over root lambda k approximation, but the running time is linear instead of exponential in k. And we also have another kind of instantiation of this trade-off between running time and approximation, which is that under conditions similar to the one where here you get constant factor approximation in time exponential in k, we can get root log k approximation in fixed polynomial time from the same relaxation used by Arora and Vazirani, by showing that when lambda k is large, a different rounding from the original Arora Vazirani one will do a better job. So I would like to end by discussing a direction that I think could lead to interesting results, although I don't have any precise conjecture to state, which is that so to find other results that justify or sort of explain the good performance of the sweep algorithm on many instances. So we have this general worst case analysis, and then the analysis that I mentioned before improves the upper bound in graphs where lambda k is large. But I think it would be really interesting to have an analysis. So this analysis fails on many interesting graphs. For example, this doesn't say anything about the cycle, even though the sweep algorithm will find an optimal cut in the cycle. So the thing is that the cycle is one of those cases where it's not the upper bound that is not tight, it's the lower bound that is not tight. In a cycle, the conductance is 1 over n, lambda 2 is 1 over n squared. So because there is a big gap between lambda 2 and phi, the upper bound gives you actually good approximation. And in fact, something like this is known for all planar graphs. It's known that in all bounded degree planar graphs, lambda 2 is order of 1 over n. It has a highly non-trivial upper bound, which means that without touching the upper bound, you immediately, on the performance on the algorithm, you immediately get that on every planar graph, the sweep algorithm will find a cut of conductance at most order of 1 over root n, which is tight for the grid, and matches the planar separator theorem in bounded degree graphs. So this is something that, so it's not saying that on every planar graph you get a good approximation, because if you have two grids connected by an edge, you're still getting a very poor approximation. But so what I think would be really interesting is to find some class of graphs on which there is a provable gap on all the graphs in the class between lambda 2 and the conductance. So then, just plugging this back into the upper bound will tell you that you have a less than quadratic loss in the algorithm. So maybe this is too much to prove. It could be that you have a class of graphs in which you can either establish a gap or show that some other algorithm will do well. Or so.
Planar you count as a good answer.
No, in a planar, like if you have two grids with one edge, the expansion will be 1 over n, and lambda 2 will be 1 over n. But maybe you can say, either some other algorithm works well, or you have a gap. Yeah, so I don't have a precise conjecture, but I think it's a direction worth investigating. I haven't really seen much of this stuff.
I mean, there's so-called Boozer inequality in manifolds that will find that direction, right? But again, under some assumption of Ritchie. I don't know. There's
No, I mean.
So far, no analog. That uses P, Cheeger H and H squared.
Yeah, but it doesn't show that you have a class of manifolds in which lambda 2 is very small. It just gives you an analog of this for manifolds in which you have a bounding curvature. Yeah, so I think it's a pretty wide open kind of question. Okay, that's all I wanted to talk about. Thanks.
Are there more questions for the plenum? I know we already had some discussion, so perhaps. Oh yes, okay.
Okay, so there's several applications of the fact that you have a large first eigenvalue when you have huge graphs of exponential size, like I think the most famous is for proximate sampling and counting when you have a self-similarity. And another application is for optimization, because you can do random walk and then cut at a random point and do random walk for the remaining graph and then cut again. And the question is, can you do something, especially for the second question? I think it might be hopeful when you have some condition on when you don't have the expansion, the necessary expansion, that you don't have the nice behavior for the first eigenvalue, but you have nice behavior for the other eigenvalue.
Well, what you can say is that, like, if say lambda k is large, that for many, or at least for some start vertices, the random walk will get to pretty high Renyi entropy fairly quickly. So then it might fail to actually mix. In fact, maybe the graph is disconnected, but that's something that potentially could be helpful.
Let's say the graph is connected, so you need some property to work hereditary whenever you say you have some objective function on the graph. So you need some property which will be for any such subgraph which is above the value of the objective function. The question is there some property in terms of the which is weaker than just the first eigenvalue will be large, that will guarantee that this type of algorithm optimize quickly?
I don't know. I mean, there are a lot of pieces to your question. You want you want a hereditary property. You want this. I don't know.
More
I mean,
than a remark than a question. So we know that if we have an objective function on a graph, a huge graph, and above any value of the attainable, the graph induced by these vertices is an expander, then we can optimize very quickly. So the question is, can we relax it if the graph above any value satisfies some weaker condition which involve the other eigenvalue?
So maybe that's a case in which those relaxations would work. So I'm not sure what's the setting that you're thinking about, but
Maybe small set
so like
expansion?
yeah. So some of the algorithms that you would say, well, so if I have constraint satisfaction problem with two variables per constraint, and the constraint graph is an expander. So in some cases you can, can do things more quickly. If instead of being an expander, lambda k is large, then you can still do something. But yeah, I don't know. I think it's different from the setting that you have in mind. So.
But it's geometric rather than algorithm. So assume that you restrict Laplacian to the invariant subspace of function of expectation 0. I mean, orthogonal to the constant function. And then you can say something about determinant. Does it translate in some natural way to the properties of the graph?
Oh, I don't know. What does it say for a manifold?
I don't know.
Ah, okay.
I also don't know, but that's just natural.
Yeah.
Because you know that this determinant will be below 1 because
If it's connected.
Geometric mean. If it's connected, if it's not connected, it will be just 0, right?
Yeah.
So the question, you restrict Laplacian to the subspace orthogonal to constant functions. To the function of expectation 0. And you can compute the determinant as well.
So the determinant
what does it
Of
tell
this
you?
map,
it's a
of
number of
this
spelling
linear map.
twists.
Really?
Ah,
Okay.
Ah,
I
you
don't know anything about
This is the matrix tree.
okay. So
But
it
no,
has
but
some.
just
Actually-
a regular case. I don't think it works for the.
No, for Laplacian it works.
No, it works in general.
No, of course a theorem works in general, but I'm not sure that being orthogonal to
No.
the concept.
Ah.
Yeah, perhaps.
Orthogonal to the one for them.
And with the relevant theorem is the matrix tree theorem.
Ninja?
If you
Ah, sorry.
Go ahead.
If you have a control on like lambda, not just on lambda 2, but on lambda k, a better control than something trivial, then can you have a better bound as a mixing time of one function? Or with lambda 2 tightly determined?
I'm not sure. I mean, you can say something different from the mixed time. So you can say, suppose the lambda 2 is not so big of the Laplacian, but lambda k is big. So then you can say that for many start vertices, the collision probability of the distribution of the random walk will go down very quickly. And it will get to something like 1 over whatever, k squared over n or k over n. That doesn't mean that the random walk is mixed, but it means its entropy has been increasing quickly. After that, to get from there to uniform, it really depends on lambda 2. In fact, the graph could be k expanders connected by just one edge between them. Right? So immediately you get to collision probability k over n, immediately, log n time. But then it will take longer to move around.
Lambda k large, it means that there is k measure that you will approach a combination of this k measure. In fact, this should provide a way to prove this k Cheeger in a probabilistic way and not in an algorithmic way.
So is a conjecture that any probabilistic way leads to an algorithm? There is a conjecture that any probabilistic argument can be algorithmic.
And a reverse also.
I know.
Do you have any structure theorem for graphs in which lambda k is large, or you don't assume anything about the gap?
Yeah, so if lambda k is large, then phi k needs to be large.
Yes.
So then, so either actually phi 2 is already large and the graph is an expander, or there has to be some I between 2 and k, such that there is a gap between I and I
Just
plus
by
1.
an averaging argument.
Yeah.
But is there anything conceivably stronger than that? I just tell you that lambda k is large, and so I don't necessarily want a partition or anything. But can you do something about it?
I mean, to me, the right sense should be if lambda k is large, and we get this up to the precise dependence on k. If lambda k is large, there is some k prime possibly smaller than k, such you can partition the vertices into k expanders.
Yes, exactly.
Yeah. So we do get this because there will be some k prime between 2 and k for which this gap is large if phi k is large.
All right, let's have some tea.
All right.
Come back and-